The overall goal of this procedure is to fabricate a backgated graphene field effect transistor decorated with Coulomb impurities for scanning tunneling microscopy and spectroscopy studies. This is accomplished by first growing monolayer graphene on an electrochemically polished copper foil and transferring it onto a hexagonal boron nitride silicon dioxide substrate. The second step is to clean the graphene hexagonal boron nitride silicon dioxide heterostructure in an argon-hydrogen environment and evaporate a gold titanium contact pad onto graphene. Next, the heterostructure is assembled into a gate-tunable device by wire bonding it onto appropriate terminals on a scanning tunneling microscope sample holder. The final step is to calibrate the scanning tunneling microscope tip on a gold 111 surface and to evaporate Coulomb impurities onto graphene in an ultra-high vacuum environment. Ultimately, scanning tunneling microscopy is used to image the Coulomb impurities on the gate-tunable graphene device and to investigate the spatially dependent electronic structure of graphene in the presence of charged impurities.
The main advantage of scanning tunneling microscopy over other methods, such as angle-resolved photoemission spectroscopy, is that it has not only high energy resolution, but also has high spatial resolution as well.
This method can test some fundamental predictions regarding the behavior of some relativistic charge carriers in response to a range of perturbations, such as the formation of atomic class resonances when effective nuclear charge of a charged impurity exceeds a certain threshold.